Good morning, I'm Tacca from Virgo and I have the great pleasure to talk about the updates from ground-based gravitational wave detectors. In particular, I will discuss the results obtained by LIGO and Virgo during the third observing run of 3, and I will introduce the upgrades that are planned for the next years. Let me first remind how a gravitational wave detector is working. Conceptually, it is a microsonde interferometer with some additional components. On this scheme, the layout of Advanced Virgo is shown, but the layout of Advanced LIGO and KAGRA are conceptually the same. In particular, there is a laser beam that is divided in two different beams that are propagating along their arms and are reflected back by some mirrors, and finally they are recombined at the same level of the beam splitter. What are the additional components that are installed in gravitational wave detectors with respect to standard microsonde interferometer? We have first very long Fabry-Perot cavities installed along the arm, and they are needed to increase the optical gain inside the experiment. And then there are two more additional mirrors. In particular, there are the so-called power recycling mirror that is installed between the laser source and the beam splitter, and it is used to re-inject inside the experiment the laser light that is reflected back towards the laser source, and it is needed to increase the circulating power. And there is the so-called signal recycling mirror installed between the beam splitter and the output photodiodes, and it is needed to enlarge and to change the shape of the bandwidth of the detector. But there are also other additional components in gravitational wave detectors. In particular, between the laser beam and the main mirrors, there is the so-called input optics that is needed to change the properties of the laser beam in order to be resonant inside the experiment. And between the signal recycling mirror and the output photodiodes, there is the so-called output optics system needed to clean up the beam coming out from the interferometer and to match it inside the output detectors. Moreover, there are other auxiliary benches that are installed inside the experiment that are hosting components and devices needed to the main control or the global control of the experiment. Let me now introduce the network of ground-based gravitational wave detectors. There are some gravitational wave detectors installed on the Earth. In particular, in the US, there are the two LIGO detectors, Hanford and Livingston. In Europe, there are two other detectors, Virgo in Italy and Geo 600 in Germany. And then in Japan, there is KAGRA that finally started its early operation in the last month. And there will be in the future another LIGO installed in India. Indeed, the LIGO India project was finally approved in the last month. Why we need a network of single interferometers? Since the sensitivity of a single interferometer is not enough to properly detect gravitational waves. So we need a network of single detectors that should act as a unique observatory. And as I said, this unique observatory is composed by all these detectors. And let me say also that there are agreements among the different observatories in order to share data, to make common analysis, to prepare common publication, in order to have common results. In particular, the first agreement between LIGO and Virgo was signed in 2007 and is still ongoing. And last year, finally, there was another agreement that was signed between LIGO, Virgo, and KAGRA, and right now also KAGRA can join the network completely. So let me remind what were the observing run that were done so far. In particular, the first observing run with the first observation ever of gravitational wave detector was done in 2015 and 2016, and it was performed by only the two LIGOS detectors. Then, from the end of 2016 Up to August 2017, there was the second observer run O2, and at the beginning there were only the two LIGO detectors, while Virgo joined the run in the last month of data taking. And in this run, I would like to remind that the first triple coincidence event was observed, and also the first BNS coalescence was observed. And then there was the third observing run, that is O3, called O3, that started on April 2019 and should have lasted up to the end of April 2020, with the planning of KAGRA that should join towards the end the run as well. But that was the original plan. To summarize, that was the original plan. The original plan was to take data for 6 months, along 6 months, in the so-called O3A part of the observing run, then stop the machines for the data taking for 1 month in order to make some commissioning to try to improve the sensitivity of the detectors, and then restart the data taking on November 2020 and end it on April 2020. So the idea was to have two periods of 6 months with a month of commissioning in between. But what happened? It happened that, as we all know, the COVID pandemic arrived. So we had to change the plans. In particular, KAGRA switched from commissioning to data taking at the end of February this year, but the sensitivity was still too low at that time to join O3. So the planning was to slightly improve the sensitivity to be able to join O3 before the end. But as I said, the pandemic arrived and we were needed to suspend the run. In particular, we suspended the run slightly more than 1 month earlier than planned. So we suspended O3B on 27 of March 2020. And all the activities in all the observatories were stopped at that time. After long discussion, LIGO and Virgo took the decision to focus at the end of this pandemic period on the upgrades planned for 4. And in this period, in particular, in 2 weeks in April, there was also 2 weeks of joint GEO-KAGRA data taking, just to make some tests and to make some astrowatch. So let me say something about O3. In particular, I would like to say that on O3A, that lasted 183 days, the duty cycle was very good. We had at least 44% of time with 3 interferometers online, and we had at least 81.9% of time where we had at least 2 interferometers online. We had only 3.2% of time where no detectors were online. And let me recall that the downtime includes also the maintenance that are needed once per week in all the detectors. The duty cycle of O3B was even better. In particular, we had 51% of time with 3 detectors online and at least 2 detectors for the 85.4% of time. The shutdown with no detectors was only 3.4% of the time. Let me just say that in this part of the run of 3B, the duty cycle of Virgo was slightly lower than the one of LIGO, since some time was dedicated to commissioning activities in order to reach a BNS range of at least 60 megaparsec. And now let me show you the performances of the instrument during this run, in particular in terms of BNS range. As you can see, the BNS range was almost constant along the whole run, and in blue there is the Livingston performances, in red there is the Hanford performance, and in purple there is the Virgo performance. As you can see, performance from Livingston were almost the same during O3A and O3B, but the performances for both LIGO Hanford and Virgo were improved during the commissioning break and in the last month of the run. And here finally we have the results, the scientific results of the run. In particular, as you can see from this graph, we had a huge amount of gravitational wave only candidates. In particular, we had 80 gravitational wave alerts, and after some studies there were 24 detections. This means that we had 56 gravitational wave only candidates that should be carefully analyzed, and this is how they were uh, observed during the 12th month of the 11th month of the run. Now an offline analysis is still in progress to confirm these candidates and maybe to find more events in all the data that were acquired during O3. Let me discuss briefly the first results that we had. In particular, on the 12th of April 2019, there was the observation of a binary black hole coalescence with really asymmetric masses. I would say that the two black holes that were merging in this event have significantly different masses. Indeed, one of the two had a mass equal to 30 solar masses, while the other one has a mass equal to 8 solar masses. It was also the first observation of gravitational wave with higher multiples, and it can give us further information about the sources and new tests. It can be also new tests for the general relativity. Moreover, this observation will also improve the knowledge on the population of black hole present. The second interesting event that was observed the 25th of April, and it was the observation of a compact binary coalescence with total mass of 3.4 solar masses. This is most likely the second BNS detected after the first one detected in August 2017. And the analysis told us that it cannot be a binary black hole or a neutron black hole coalescence. Unfortunately, there were no electromagnetic counterparts for this event, since it was more distant and less well localized, in particular since it was only a two interferometer detection. Only Livingston and Virgo were online at that time. An interesting result for this event is that the total mass is the larger than any known system so far. And the main question that we are asking is this the hint of a new population present in the universe? And then I would like to introduce also a third interesting result. That is these gravitational waves observed on the 14th of August last year from a coalescence for a 23 solar mass black hole and a compact object with a solar mass equal to 2.6 solar masses. And we have a certain nature of this second component. It could be either the lightest black hole or the heaviest neutron star even observed. Another interesting result is that the mass ratio between these two events is really high. It's 9 to 1. And also multiple emission was observed, and there were in the analysis clear evidence of the inclination. So this will be a challenge for formation models and to improve all the models. But these are so far the only public results, but more results will come, in particular with 56 gravitational wave alert. There will be for sure new issues of the gravitational wave transient catalog, and there will be some special paper focused on special and particular events, and there will be also new companion papers. I would like to say also that the search of gravitational wave event is still ongoing on the full O3 dataset, so we can have many more events that are hidden inside this data. I would like also to say that LIGO and Virgo data become public after an initial proprietary period. In particular, the data around an exceptional event are made public just after the publication of the associated paper, and there are chunks of 6 months that are published 18 months after the end of the data taking. I would suggest to visit this website, that is the website of the Gravitational Wave Open Science Center, where all the information are present about the open data. But what will happen right now? As I said, the shutdown period between 03 and 04 is focused in the upgrades of the current detectors. In particular, we would like to build the so-called Advanced Plus detector, Advanced LIGO Plus and Advanced Virgo Plus. And the idea is to have 4 detectors online for 04, the 2 LIGO detectors, Virgo and KAGRA. There is a huge question mark, that is how long will be the period between 03 and 04, since obviously it is impacted by the COVID pandemic, and the real impact and the real delay that is introduced by the pandemic is actively studied right now. So we still don't have a clear answer to a clear vision about that. Let me say a few words about the upgrades that are planned in Virgo, in LIGO, and in KAGRA. In particular, I will start talking about Advanced Virgo Plus, that is a 2 phases project. There will be phase 1, that is the detector that will be built for 04, and the phase 2, that is the detector that will be for 05. During the phase 1, the signal recycling mirror will be installed. Indeed, Virgo has not yet the signal recycling mirror installed during the previous observing run. The input power will be increased up to 40 watt, and there will be the installation of the complete frequency-dependent squeezing system that will allow us to reduce the impact of the quantum noise in all the bandwidth. Finally, also a system of seismic sensor will be installed around the test masses in order to implement the cancellation of the Newtonian noise. For the phase 2, a further increase of the laser power is planned, and the laser power will be of 60 watt or more. And moreover, the most important change will be that the laser beam and the test masses will be increased. In particular, we will have a beam radius of about 10 centimeters on the end test masses, and also the test masses will be much heavier than today, and they will arrive to be at up 100 kilograms. The next important upgrade is that we will try to have better coating characterized by lower mechanical losses, fewer point defects, and better uniformity in order to reduce the impact of the thermal noise. In the next slide, there is the target sensitivity for the phase 1 in light blue, and the target sensitivity for the phase 2 of Advanced Virgo in light red, compared to the current sensitivity that we had during 03. As you can see, we would like to improve the sensitivity along the whole bandwidth, and in particular, as I said, in phase 1 we would like to reduce the quantum noise, while in the phase 2 we would like to push down the thermal noise wall. Now a few words about the upgrades that are planned for LIGO and for Advanced LIGO Plus. Also, Advanced LIGO Plus is a two-phase installation plan. Some installations that are planned before 04 and some installations that are planned after 04. In particular, before 04, LIGO people would like to build all the changes in the buildings that are hosting the experiment. They will install some adaptive wavefront control in order to improve the mode matching and other optical properties of the experiment. They will install as well the frequency-dependent squeezing, and they would like to improve the overall optical efficiency inside the experiment. While after 04, they would like to install larger beam splitters with a diameter up to 45 centimeters. They would like to change the readout system installed in the balanced homodyne detector, and also LIGO would like to have better coatings with the same properties that are searched for the Virgo coatings. Here is a plot with the sensitivity of the Advanced LIGO, the target one, and Advanced LIGO Plus target sensitivity compared with the Advanced LIGO sensitivity that was recorded during O3. Also for LIGO, the main target will be to reduce the quantum noise before O4 and to reduce the thermal noise before O5. Now a few words also about KAGRA. KAGRA, as I said before, KAGRA was very close to the target sensitivity to join O3, but the operation was stopped by the pandemic, unfortunately. So there are some upgrades that are planned before O4. In particular, they would like to control the signal recycling mirror that was installed but not really well controlled in the past, and they would like to have some upgrades on the suspension, in particular, in almost all the parts of the suspension. They would like to upgrade the software, they would like to upgrade the sensor, they would like to fix some hardware, and they would like finally to improve the control of the suspension. They will also try to improve the cryogenic system. Indeed, let me recall that KAGRA is the first underground cryogenic detector, in the sense that it is built underground and the test masses are at cryogenic temperature. And they would like also to upgrade the hardware used for the calibration. In view of R5, there is if it is possible, they would like to replace the input test masses. And here the sensitivity, the target sensitivity for KAGRA is shown on this plot. In particular, it is the black curve and is compared with the best sensitivity achieved by KAGRA so far in this pink-purple curve. Now I would like also to say a few words about the third generation detectors, in the sense that Advanced Plus detectors are a step toward the third generation detector. And the third generation detectors will have some, let's say, a complementary approach and a common technology on what we are trying to develop for the Advanced Plus detector. And in particular, as you know, there is the plan to have at least 2 detectors for the third generation. Einstein Telescope in Europe, which will be underground, will probably have a triangular shape with multiple detectors, one cryogenic for the low frequencies and one not cryogenic with high power to detect the high frequency. And there will be another detector, Cosmic Explorer in the United States, that will have a 10 times longer L shape, and it will be divided in 2 stages. In particular, in the first stage it will work at room temperature, while for the second stage they are considering the possibility to have the detector working at cryogenic temperature. I would like to show in this plot how and what the third generation detector can do with respect, for instance, to Advanced LIGO right now. In green and in pink, there are the target sensitivity in terms of redshift and total source frame masses versus the total source frame masses for Cosmic Explorer and Einstein Telescope. And as you can see, the possibility to detect redshifts will be much higher with the third generation detector with respect to what we can do right now with the advanced detectors. I would like to give also a few words about the timeline, both for Einstein Telescope and Cosmic Explorer. Einstein Telescope, the conceptual design and the idea of the Einstein Telescope were done in the past, in the last 10 years, and now there is a proposal that will be submitted in the next months to the European Union in order to have funds to build the infrastructure. The site for this experiment will be decided in the next years, and the main target is to start the construction in the second half of the 2020s in order to be operational, let's say around 2023, 2020, 2033, 2034. There is a similar timeline also for Cosmic Explorer. In particular, now Cosmic Explorer, the science case and the technical study are made right now. And then the idea is to have the technical design of the detector. And as I said before, Cosmic Explorer will probably divide in two different stages, and the perspective is to start observing in parallel with Einstein Telescope in 2034, 2035. So, to draw some conclusion, I would like to say that despite the early conclusion due to the pandemic, O3 has been a tremendous success with 56 new gravitational wave candidates. In particular, so far we were able to observe a binary black hole system with very asymmetric masses. We were able to observe a second binary neutron star with a total mass of about 3.4 solar masses, and we observed the coalescence between a black hole with an uncertain compact object. Moreover, we can say that the installation of upgrades in the detector is in progress, and higher sensitivities are foreseen for 4. And let me say and remind that this new detector, the Advanced Plus detector, will be a key step towards the third generation detector that will be installed in the next years. So thank you for your attention.